Welcome. I am Mahendra Shetty, lecturer in Chemical Engineering, Kekewak Polytechnic, Nasik. The Department of Chemical Engineering is one of the accredited departments by National Board of Accreditation, New Delhi. In this session, we are going to study the Bernoullis Theorem. The statement of Bernoullis Theorem is for an incompressible, steady and inviscid fluid flow, the total mechanical energy of the fluid is constant. The total mechanical energy represents the summation of pressure energy, gravitational potential energy, and kinetic energy. And the summation of all these three energies remain constant. The mathematical statement of Bernoullis theorem is P upon rho plus Gz plus U square upon 2 is equal to constant. The first term, that is P upon rho, is a pressure energy. The second term, Gz, represents the gravitational potential energy, and the third term, that is U square upon 2, represents the kinetic energy. The unit of each term is joule per kg, that is energy per unit mass. The Bernoulli statement can be represented in mathematical form in alternate way as P upon rho g plus z plus u square upon 2g is equal to constant. In this case, the unit of each term is in the form energy per unit weight. It is represented in the form of unit of length, that is meter, and it also called as head. While deriving the Bernoulli's equation, we have to assume the flow is steady, means it does not vary with time. The flowing fluid is incompressible, means the volume of the fluid remains constant. The fluid is flowing along a streamline. The flow is irrotational, means the molecule of the fluid does not revolve around their axis. And the last one, the fluid is inviscid, means the fluid have a zero viscosity, means it does not have internal resistance to flow. The basis for deriving the equation is the Newton's second law of motion, which states that force is equal to the change in momentum per change in time. The change in momentum per change in time is nothing but the rate of change of momentum. Let us consider the smallest element of a fluid having motion in diagonally upward direction. The unit length is delta L. The lower end of the element is at distance z from a datum line, and the elevated end of the fluid element at a height of z plus delta z from datum line. The pressure in the direction of flow is applied for transportation of this fluid element in the direction of motion. So the force acting in the direction of motion will be P into A, and the opposite force, that is P plus delta P into A. The self weight of this fluid element also impose a force in the direction of flow due to its weight, that is rho A delta L into G. Let us consider the velocity at entrance be u and at exit be u plus delta u. Now, the forces acting on fluid elements will be: the first force is in the direction of motion, that is P into A. We will consider it as a positive. The second force will be in opposite direction to the motion, that is P plus delta P into A, and we will consider it as a negative as it acts in the opposite of direction of motion, and the force due to weight of a fluid element, the weight is rho A delta L G, and cos theta will be the component of that weight in the direction of motion, and it acts in opposite direction. That's why we have taken it as negative. So the all forces acting on a fluid element, and if we consider the summation of these forces, then we will get first force, that is PA, which is acting in the direction of motion, so we will consider it as positive. The second force in the opposite direction, that is P plus delta P into area, and it will act in opposite direction, so we will consider it as negative. And the third force due to weight of the fluid element, so it will be rho A delta L G cos theta. So it will again act in opposite direction of motion, so we will consider it as negative. So as per Newton's second law of motion, the summation of these forces will be equal to the rate of change of momentum, and the rate of change of momentum is represented as mass flow rate into rate of change of velocity, that is u plus delta u. This is the final velocity minus initial velocity, that is u, as the velocity term having positive sign and negative sign, so the effect will be 0, and this will reduce to m dot delta u. So m dot delta u is the mass flow rate, and we will convert it from the volumetric flow rate as rho A into U. So A into U is a volumetric flow rate, and if we multiply it by a density, then it will be converted into mass flow rate into delta U. So if we consider it, the left hand side, PA and minus P into A will get cancelled, and the remaining term will be delta P into A minus rho A delta L G. Now this cos theta can be considered as the effect of weight in a direction of motion. So the cos theta, the distance is delta Z and the diagonal is delta L. So the cos theta will get converted into delta Z by delta L. So we can replace this cos theta by delta Z upon delta L. So cos theta is replaced by delta Z upon delta L. So if we rearrange this equation, the final equation will become delta P into A plus rho A delta L G delta Z upon delta L plus rho A U delta U and is equal to 0. So if we divide the both side of this equation by the term rho A delta L, rho A delta L so this area term here will get cancelled, rho area and delta L will get cancelled, here rho area term will get cancelled. So the resulting equation will be delta P upon rho into delta L plus delta Z into G upon delta L plus U into delta U upon delta L is equal to 0. So again, if we multiply this equation by delta L, then it will reduce to delta P upon rho plus G into delta Z plus U into delta U is equal to 0. If we represent this equation in differential form, it will be converted as dP upon rho plus G into delta Z plus U into du is equal to 0. And after integrating this equation, we will get P upon rho plus G into Z plus U square upon 2, and the integration of 0 will be constant. So this is the required equation of Bernoullis theorem, that is the summation of pressure energy plus gravitational potential energy plus the kinetic energy is constant. So the equation of Bernoullis theorem is P upon rho plus Gz plus U square upon 2 is equal to constant. If we have to use these equations for 2 points, that is 2 stations, it will be converted as P1 upon rho plus Gz1 plus U1 square upon 2 is equal to P2 upon rho plus Gz2 plus U2 square upon 2, where 1 and 2 represents the condition of the fluid at station 1 and station 2 respectively. The Bernoullis theorem is for the inviscid fluid, means for the frictionless fluid. So for real fluids, the Bernoullis equation will be as P1 upon rho plus Gz1 plus alpha 1 U1 square upon 2 is equal to P2 rho plus Gz2 plus alpha 2 U2 square upon 2 plus HF, where alpha 1 and alpha 2 are the correction factor for kinetic energy and HF is correction factor for the friction of the fluid through pipeline. Thank you.